I was Jennifer Baby.
Okay. Ciao, good afternoon. I apologize for 5 minutes delay. I hope that everyone can listen to me remotely. Otherwise, please let me know on the chat. I will make an effort to monitor the chat. Let me see, with some periodicity. Okay, very good. No messages so far. Okay. So, questions? Nothing? Okay. Let's agree that before the break, I open a question and answer session, and you are obliged to ask at least 2 questions, okay? Related to what I'm presenting today, what I presented earlier, okay? We don't break the break if you don't ask 2 questions, okay? And if I cannot reply to your question because I don't know the answer, then double break, okay? And okay, double break is not really fair because I was already late, but let's say that I may offer you a coffee if I cannot answer your question, provided the question is, approved, okay? And okay, that's it. So it's quite warm today. So what are we talking about? We are talking about climate system. Science of climate change means that we have to talk about the climate system. And in particular, we need to move forward towards understanding how we model the climate system. Because modeling means predictions and means to devise action, to devise our reaction, to strategize our reaction to that. So we are setting the basis for the science, for the theory and the models. And therefore, we talked about, you may remember, data, because data are needed for setting up models. We talked about drivers, and in particular emissions, and other drivers, which means input data, basically input to models, forcing, okay, to the climate system. And then we started talking about the structure of these models. These models are mathematical models, and therefore they have to be based over equations. And the equations can be, as we said, based on the laws of physics, the laws of chemistry also, not only physics. In particular, if we study the dynamics of pollutants and chemical reaction that may occur in the atmosphere. And we already mentioned that some statistical laws may also be included. Why statistics? Statistics in the past, it was used, just a recap to better understand what are the disciplines that we are invoking. Statistics was used in the past to provide models for the phenomena that we cannot describe basing on analytical relationships. I mean, also statistics is made by analytical relationship, but the non-statistical models or deterministic models are based on the laws of physics, laws of chemistry. When we cannot explain these processes by using the theory of deterministic disciplines like physics, chemistry, then we use statistics. And in the past, this was the use of statistics. Today, actually, statistics is also invoked because we recognize the presence of uncertainty. You may remember we discussed a lot uncertainty in climate modeling. And so one way to describe uncertainty and to recognize uncertainty as a fundamental component of the climate system, we need to find the disciplines that deals with the treatment of uncertainty. And one possibility is statistics. So we started discussing these laws, which, when we put them together, form a mathematical model. And we closed the last lecture by talking about the complexity of these processes and therefore complexity of models. And we talked about nonlinearities, and we defined what is a linear relationship. And you can see on the screen the two conditions. The screen is not really bring it down a little bit. I just have to see where not here. So let me look at the other space there. It's here. Yeah. Oops. What happens? So let me check. Okay. We talked about the two conditions for defining linearity, which also implies a superposition principle. Please remember these two conditions because the definition of linearity is extremely important to understand the science of climate change. And given that it's extremely important and given that it's very specific, you may find it as a question in your final quiz. So I said may because the quiz is composed by questions that are chosen by chance, but for sure, in the overall pool of questions, there is the definition of linearity, okay? And the reason why this is included is that linearity is indeed, linearity and nonlinearity has a fundamental role in the climate system. When you talk about processes, and there are some processes that are quasi-linear, quasi means almost linear, or linear, actually, I don't remember any example of a purely linear process, but there are processes that are close to linear. They are, in a way, simpler to model. The complexity is reduced. When there are processes which are characterized by threshold tipping points, so which means that for a small, tiny change in the forcing, there might be a huge change in the result. This is when nonlinearity comes in. And keep it in mind because it is extremely important. The climate system is such that we know, in some cases, tiny change in the forcing, which means, for instance, a tiny change in the concentration of CO2 or a tiny change in rainfall forcing over an area that is subject to flooding, it may happen that a tiny change in the forcing implies a huge change in the final result and a huge change in impact. So there are situations where a tiny change in extreme rainfall, strong rainfall, intensive rainfall means that you get a big difference in the impact of the flood. Think, for instance, at the flood that is originated by overtopping of a levee, which means that a very large area is suddenly flooded. You understand that a difference of 1 centimeter in water level means overtopping or not. And when you get overtopping, it's not only that 1 centimeter of water that goes out. Overtopping means that the levee gets destroyed, and suddenly, for a change of 1 centimeter of water level, you get a huge flooded area. So this means nonlinearity. This means amplification of the drivers. And you understand that it is extremely important for us to understand these processes and to be able to predict them. For what reason? Climate change in some locations is not a problem, and in other locations, even a tiny climate change is a huge problem. We have to understand these conditions if we want to adapt to climate change, if we want to recognize what are the priorities for intervention. So this is why linearity is important. Okay, you have gained 1 bonus for the final question and answer session, please.
It's just a general question.
Yeah.
These slides are found online somewhere.
Yes. This one, I tell you where. If you go on my website, where I found it today, actually. So this is the lecture Earth System, which is listed here in this list. So you go Earth System. This is the web page of our course. Okay, the Earth System. and you get the extended lecture where there is the definition of linearity somewhere here. There is, you see here, box non-linearity. And then if you go in the bottom of the page, download the PowerPoint presentation and you get to here. Okay. Okay.
On page 2, but for me it's just.
If you go to the bottom of the page,
There's. But the other lecture account was on the page.
I think here is what we saw. Let me see if I can show me the web address, because I think here it went to the web address of the picture. So it's the same here. I think it is a visualization problem because I'm not logged in my website here. So yeah, the address is correct, but I think it must be a visualization problem. I don't really know why. And at least if the problem is shared by others, just let me know. I shouldn't be like that. And in the break, maybe that we can try to solve it. Try to reload for now.
Yeah,
It doesn't work. Okay. Okay, so we can have a look later. Okay, so I just want to emphasize once again what is the superposition principle. You can find our references on the web, in particular to Wikipedia. There is a link, I think, in the web page about the superposition principle. The superposition principle means precisely the first condition for linearity, which means superposition principle means that if you have a forcing to a system that you can split in two parts, like for instance, a rainfall that is given by a first rainfall event plus a second rainfall event. Okay, so you get a rainfall event that is composed by two impulses of rainfall. The effect of the two impulses of rainfall is equal to the sum of the individual effect of each impulse, of each rainfall spot. Okay, this is clearly not true. You know the proverb that say it rains over the wet soil, it rains over the wet land, which means that when you get a rain over a land that is dry, you have a different result in terms of, for instance, river flow, for instance, flooding, with respect to a situation where the same rainfall occurs over a land that is completely wet. This means that if wetness, which means previous rainfall, is important, it means that for the effect of rainfall over flooding, the superposition principle doesn't work. Okay? Because if you get two separate rainfall over a dry terrain, the sum of their effect is not the same of having the sum of the two rainfalls over the same terrain, because after the first rainfall, the terrain gets wet. So remember the superposition principle, which in general doesn't apply in climate processes. Otherwise, we wouldn't have any amplification. When I say a small tiny change in the driver may imply a big change in the final result, it means that the superposition principle doesn't work, because the tiny change is superimposed to a previous condition that is preparing, getting close to the threshold, getting close to the tipping point. Just try to understand what means complexity, what means linearity, what means non-linearity, and what does tipping points mean. Means non-linearity and complexity. Keep in mind that complexity also involves uncertainty. So when we model linear processes, uncertainty is reduced with respect to a situation where there is a strong nonlinearity. So this is why the climate system is complicated, because it's highly nonlinear. Okay, and we already talked about tipping points in the Earth system and in the societal system. which means non-linearity. We already talked about these two slides, so let's move forward. So what kind of models are we talking about then at the end of the story? Complex models, mathematical models, based on possibly on the laws of physics, mainly chemistry in a second priority, and statistics in a second priority. But these models can be very different each other. And this may seem like something that it's not so clear. So why models can be very different? They are representing the same process. They are representing the same system. They are representing climate. So the model should be one. Why many models? Many models because what we represent with the model is not the reality. The digital twin, this is a buzzword nowadays, the digital twin is considered to be only one. But actually, the digital twin is an approximation. It's not a replicate of the prototype. The prototype is the real system. It's impossible, you understand? That is clearly impossible. Any lab experiment, and with the lab, I mean both the physical model, the small scale models. Sometimes when we have to study part of the Earth system, we can make a small scale model in the lab. If we want to study how a river flows, we reproduce the river in the lab in a small scale. But again, even with these models that look very similar to the reality, just in a smaller scale, they are an approximation. And mathematical models, even more, they are approximations. And therefore, depending on the approximation that you make, the model is different. So the approximation may be, for instance, to think that there is no feedback between larger evaporation and through the clouds, a reduction of the solar radiation. We assume that there is no feedback. Okay, so if we assume that there is an increase of temperature, larger evaporation, which means a higher water content in the atmosphere, we assume that this is not creating clouds, it's not acting as a screen against solar radiation. This is a negative feedback. It means that clouds are reducing, contributing to reduce the temperature. A model may just neglect this for many reasons, okay? And therefore, if we make assumptions in order to approximate, in a way, our representation, to approximate is a necessity, you make assumptions, and then, depending on the assumptions, you get a different model. What may be the reason for making this assumption? Many, as I said, many reasons in order to simplify the representation. One reason is lack of knowledge. We don't know feedbacks, and therefore we assume that there are no feedback. This is a possibility, a possible reason. Another reason may be that I want a simple model. Why? Because I want, for instance, to reduce computational time. And therefore, I want to make a model simpler. And therefore, I assume that some feedbacks are not there. I assume that some processes are negligible. This is the second reason to make a simplification. A third reason may be that I want a model that is purely statistical and not physically based. Why? For instance, because I want to estimate uncertainty. And therefore, I use a model that is not based on the laws of physics, but it's based on the laws of statistics. So instead of using a deductive approach, like I start from the theory, I start from my knowledge, I start from the laws of physics, and I build a model. In statistics, what I do is I look at the data, the final result, and I just make a model that explains the data, explains the reality, without starting from the laws of physics, but starting from the laws of statistics. If you think of tossing a coin, if I want to reproduce the result, I may build a physical model where I consider the body, the coin, that is tossed with a given force and with a given initial condition, like the height of my hand when I toss the coin. So I represent everything with the laws of physics. We know everything of tossing a coin. So this is possible. In principle, it is possible. We know everything. On the other hand, we know that in practical terms, it's not possible because it's impossible to describe with a clear, with the full precision, the position of the hand, the forcing of the thumb to the coin. It's impossible to describe precisely, even if I put a sensor there. You understand? It's impossible. And therefore, it makes the result unpredictable with a deterministic model, with a physical model. So what is the solution? The solution is just that I flip the coin like 10 times, and I understand that with a probability of 50%, I get a net. And this is a statistical description, which is more useful. I look at the results, and I build a model that reproduces the outcome, recognizing uncertainty. Because you may say, okay, but it's not a real prediction, because I cannot predict for each in terms of probability, I cannot predict for each flip of the coin the final result. Indeed, I cannot. But I cannot because it's impossible. So statistics recognize the uncertainty and models it, which is very useful. So this is why when we flip the coin, we try to stick on a statistical description. You know that in the narrative of gambling, there are people who believe, in the narrative, I mean, if you look at the literature of it, there are people who believe that basing on perception, feeling, some gamblers may elaborate a prediction that is not statistical. Like, I feel that in the next roulette round, I think that the number is 35. Okay? There were several studies. You know, the roulette is 36 numbers, so the probability of getting 35 is 1/36. Okay? Statistically, this is the explanation. There were several studies, scientifically based, that interviewed professional gamblers and checked if their feeling, their kind of prediction outperformed statistics. The result was no. Okay? No. So, in some cases, it's impossible to make a prediction that is deterministic, and in these cases, statistics is extremely important. In climate, we know that it's impossible to get a fully deterministic prediction, so involving statistics is extremely important if you want to model that part of uncertainty. So, once again, it's useful to try to make a classification, the simplest possible, of models for the climate system. It helps us to understand what kind of models we are talking about. And then here you see a first difference between process-based models and empirical models. By the way, when you look at these classifications, just keep in mind that classifications are never black or white. There is always a gray zone, okay? And classifications are not completely independent. So, for instance, statistical models can be considered part of the empirical models. In a way, empirical models are those that look at the results and try to interpret the result with an empirical equation. It's not physically based, it's an empirical equation. And the empirical equation can be statistically based. Okay? Process-based models are a synonym for deterministic models. They start from the laws of physics and chemistry. Laws that are analytically expressed and supposed to be precise. Okay. Once again, I want to remind you that a deterministic model for a given input produces always the same output. A statistical model, instead, for a given input produces the same output in probabilistic terms. Okay, so it is very simple to make the difference, to mark the difference between a deterministic process-based or physically based model and a statistical model. Once again, deterministic model, one input, one output. Okay, statistical model, one input, one probability distribution of the output. It's a different story. Okay, statistical models give you a probability distribution, don't give you a precise outcome. Okay, so you can understand the difference. Process-based means based on precise equations. Empirical models, again, precise equations, but not based on a particular discipline, physics, chemistry, just whatever relationship that explains the output without invoking physics, chemistry, whatever. Okay. Another separation, which is very similar, deterministic models, and they are basically part of these process-based models, and stochastic models. Stochastic, let's say, in a simple language, that stochastic is synonym of statistics. Okay, I tell you the difference, but for now, just start from this baseline. Stochastic is synonym of statistics. Okay, let's start from this baseline. So, deterministic and statistical models and other classification. They are very similar, but in empirical models, you can have statistical models, but also other models. And same thing for deterministic and process-based. A climate scientist would propose many other classifications, like global models, which reproduce the whole climate system, and regional models, which reproduce the climate over a region. Okay. This is another classification which I'm not mentioning here, because I don't want to focus too much over modeling, but just want to tell you that a climate scientist would say more than that, okay, more than this. And another classification that I learned recently, because recently the literature proposed this evolution of climate models, it's between convection permitting models and non-convection permitting models. This means that in the treatment of rainfall, you consider convection, which is extremely important to describe summer storms, for instance, very short duration events. Convection is very turbulent, so it's characterized by a high turbulence. So, I mean, this is a recent evolution of climate models. It's still an attempt. It looks like in the modeling of thunderstorms, indeed, these models perform better. They have to work on fire resolution. Fire resolution, I mean something like 3 kilometers or 1 kilometer. So the square grid is 1 kilometer in size, 3 kilometers, which means that they need supercomputers. And they can be applied only at the regional scale, not global. Okay. Keep in mind that it's a fascinating attempt to try to, create a model of the climate system, a possibly global model. It's really a fascinating ambition, and it's really interdisciplinary, possibly transdisciplinary, so possibly needing new disciplines. We still have a lot to do in this direction. So interdisciplinarity, actually, I could give you several examples where really interdisciplinarity cannot be really reached. So, for instance, an example that I may give, the models of the water cycle, hydrological models, necessarily are part of the climate system and therefore should be part of the climate models. But actually, the effort towards the modeling of the hydrological cycle by hydrologists and climate scientists really very rarely find a convergence. So these are more often traveling along parallel routes with no intersection. And this is a bit of a problem. It's a bit of a problem because you understand that even when communicating the results, if you have two communities working on a global model and sub-models, hydrological models are sub-models of the climate system, and these two communities don't reach a convergence, so they present their results autonomously, independently, you understand that both in terms of credibility, both in terms of and also in terms of probability of success, it is a negative fact that we cannot reach convergence. We already discussed of the reasons why it's difficult to reach a convergence, but actually this is also one of the reasons why climate science was not very effective in communicating their findings in the past 30 years. Okay, here there is a slide that marks the difference between deterministic and stochastic models. Okay, before I comment on the slide, which is saying things that I already anticipated, let me just say a bit more about these two terms, statistics and stochastics, which the baseline, I said they are synonyms. Actually, there is a difference. So when we say statistics, we mean the modeling of a single outcome, typically, like tossing a coin. So I toss a coin, and this is one single outcome. And then it's a typical case of statistical modelings. And then statistics may use the theory of probability, and probability is a sub-branch of statistics, but let's not to get into many details. Statistical model means typically one outcome. If I want to model the outcome from 10 coin flop, 10 coin tosses, then I get into the domain of stochastics. So if I want to model the average temperature in a year is statistics. If I want to model the temperature every day of that year, then we get into the domain of stochastics. Stochastic means modeling multiple outcomes. This is basically the difference. And for this reason, I say, okay, at our level of study, we can treat them as synonyms because the difference is really technical, okay? So I said deterministic model, one-to-one, no uncertainty, and you see there is an input and there is an output that is precise. Here, I have an input. By the way, the input can be uncertain, and I get an output that is not precise. You see the gray band. So basically, it means that there is no fixed relationship between input and output. The same input can give different outputs. This means uncertainty, this means statistics and a stochastic model. So when you apply a statistical model, once again, you have to expect not a precise description of the output, but a precise description of its probability distribution. And keep in mind that when we need to make strategies when we need to cope with climate change, with climate change mitigation adaptation, we don't need a precise prediction. If we get an uncertain prediction, provided that uncertainty is estimated, it's perfectly fine. Perfectly fine. I mean, I don't need a precise prediction of the amount of rainfall tomorrow in Bologna. If I get that I may get 10 centimeters of rain with a probability of 90%, that's fine. It's perfectly fine to make a strategy, in a way, to prepare an emergency plan. I mean, if this 90% is well estimated, it's fine. It's like predicting the intensity of an earthquake. I mean, nobody's able to predict in deterministic terms to say, okay, before 2100 in Bologna, we will get an earthquake with a magnitude of 5. It's impossible. But if we were able to say, before 2100, there is a probability of 30% in Bologna to get an earthquake with a magnitude of 5, this is perfect. Because with this probability, I can estimate the expected damage. I can estimate the expected benefit if I promote, like, a renovation of the buildings. And I mean, when we have an expectation, it's perfect. When we take decision in our everyday life, if we have an expectation, it's perfect. It's all what we need. I mean, all what we need. I mean, if you know that if you take the car and go along the highways, you have 90% of probability of making an accident, you don't take the car. If you are said that if you board on an airplane, you have 1/1 million probability that the airplane crashes, you take the airplane because it's a risk that is much lower than the risk that you run when you take your car, when you take your motorbike. If they told you, you take an airplane and 50% of probability there is a crash, you don't take it. It's clear. Because you compare with other risks. And we are all used to do that without using statistics. And this is what we need. I mean, there is no problem in uncertainty if it is estimated. It is when you don't know. Would you take an airplane if one say, I don't know, what is the probability of a crash? You wouldn't take it. And you may lose an opportunity. Or at least I wouldn't take it. If nobody was able to tell me what is the probability of crashing, I wouldn't take the airplane. Okay, I already talked about uncertainty, so let's forget it, this slide, because this is something that I already commented. Here there is a link to the ethics. Keep in mind that ethics, it's extremely important when you make science, when you make any kind of human relationship. Ethics is extremely important. Ethics is something that is not fixed. Of course, it is something that is evolving, something that may be questioned to some extent, something that may be debatable. But on the other hand, it's extremely important that we agree that we need in any of our human activities some principles of which basically inform us on the behaviors that the humanity believes are acceptable, and also the professional behaviors that we should always keep in mind. There is, I mean, the University of Bologna has an ethical code, we already mentioned it, and any profession has an ethical code. It is just, just something that we have to know. And look at the central sentence here. Uncertainty is an essential information. We know that. It has to be estimated by using an objective method, following ethics, namely by requiring honesty, impartiality, fairness, and equity, and hold paramount the safety, health, and welfare of the public. This looks like naive. But actually, when we work with the climate system, when we work with Earth system models, I mean, there is uncertainty, and in some cases it's not always clear how to estimate it. And then if you make a mistake, as we said several times, maybe that we have to defend what we did, and it is to defend what you did. It's easier if the approach was, like it's written here, honest, impartial, fair, and etc. If you make an impartial, fair use of the data, of the information, that's it. Okay. I mean, why this slide? Because it's clear that the climate system is subjected to perturbations. This is clear. So why this slide? Because perturbations can have two origins. Can be given by natural perturbations, can be given by human perturbations, and it makes a big difference. It makes a big difference because it makes also a big difference in modeling, actually, because when you build a model, you make assumptions, as we already discussed, as we already mentioned, and these assumptions are also related to the human activity. I mean, when we represent into a climate model the carbon cycle, we make assumptions on the feedbacks, on the carbon sinks, which means how much carbon is absorbed by vegetation. Sometimes we don't have precise information. We have to make assumptions. And so the way we deal with human disturbances and natural disturbances, like a volcanic eruption, is natural. Okay. It makes a difference in terms of the results. So it is extremely important that into a system that is in permanent transition, like the climate system is never stable. We never lived under a constant climate. You understand that in this system that is in permanent transition, it is important that we recognize what are the transitions originated by nature and what are the transitions originated by humans. Why it is important? Because the solutions are different. If it is a human perturbation that is causing an increase of flooding in Bologna and the frequency of flooding, the solution is different with respect to a natural reason that is causing an increase in extreme rainfall. So this is why this slide is there. But we already talked about drivers, so it is not new what is presented here. And there is an interesting thing that I wanted to mention to you, which is the variation of the magnetic field. I think it is an interesting example because this is another unknown of our knowledge. It is another gap in our knowledge of the Earth system. So the magnetic field is continuously changing, and sometimes it happens that there is a complete flip of the magnetic field, an inversion of the poles. And this is something that Earth scientists are studying. It is continuously the subject of several research efforts, because it is unclear what is causing this flip. The flip is not really a disaster. It happened during the history of Earth. I don't remember when it was the last time, but if you look over the web, you find the information. The documented last time when there was a flip of the magnetic field. And it is something that sometimes occurs, probably for reasons related to the internal circulation of the masses of iron in the core of the Earth. And it is something that it is believed to have a strong influence on the climate. So, I mean, wouldn't be a reason of human extinction, a flip of the magnetic field, but probably would be a reason of changes in climate. And this is something that we cannot represent, we cannot predict. It's another example of tipping point. Okay. We already talked about the several disciplines, so I'm skipping this slide here. The several disciplines that are interacting, and that's it. So now we are ready for starting discussing about models. So to get into more details in how these models are done. Questions? Yeah? Okay, I can address you to some references. And actually, I had an interesting conversation with a colleague that is working. Better to say he was because he's retired. On this researches who explained to me, but I didn't include anything here and I didn't make a relevant study. But your question is interesting. So switch magnetic field. First of all, let me see if there is a Wikipedia page. Yes, geomagnetic reversal. Okay, and let me just increase it. Or maybe it is linked in my web pages. Is a change in planet's dipole magnetic field such that the position of the magnetic north and magnetic south are interchanged. And you see the Earth's magnetic field has alternated between periods of normal polarity, in which the predominant direction of the field was same as today, and reverse polarity. Okay, reversal occurrences are statistically random. There have been at least 123 reversals over the last 83 million years. So it's about one every 500,000, okay? On average, once every 450,000 years. The latest occurred, okay, more than the average years ago. So it may occur. It may occur, okay? With widely varying estimates of how quickly, okay? And there is, I think, about the consequences, let me check. History. Observing geomagnetic superconductors, just 1 second, statistical properties, chart of transition, causes, effect on the biosphere. Okay. So you see that they also studied if they are related, linked to extinction events. And so basically there are several unknowns, but I think it was mentioned by my colleagues that this may be the problem. So if the Earth field disappears entirely during the reversal, then it may be a problem, because the magnetic field is also a screen against the solar radiation. So indeed, if you get a period of in which it disappears, this could be a problem, and it is explained here. They argue that the atmosphere of Mars may have been eroded away by the solar wind because it had no magnetic field to protect it. So you understand that in this case, the consequence may be, they predict that ions would be stripped away from the Earth's atmosphere above 100 kilometers. So, I mean, yes, can be quite, but actually my colleagues said, you know, this is really a pessimistic prediction because it is possible, but he said, we have good information to be able to conclude that life didn't disappear, of course, during these magnetic reversals. Yes, maybe that there is a mass extinction because it may cause a climate change. And I don't remember what it told me, but I believe, I hope the information is enough. But of course, you get a lot of information here. But keep in mind that, I mean, for sure, as I already mentioned in my first lecture, for sure, the Earth system is not eternal. So there will be one day in which the magnetic field will disappear, because this is the normal fate of planets. We are studying Mars now because we want to understand how this occurred over Mars. But Mars had an atmosphere, had a lot of water, and then everything disappeared, probably because of the cheese of the magnetic field. Okay, that's it. Other questions? I mean, I understand that when one talks about uncertainty, about unknowns, and I put the accent on that. I really stress uncertainty, unknowns. I have colleagues that are more optimistic, and they say, look, these unknowns will disappear. We will get to a level of knowledge, humanity will get to a level of knowledge in which we will understand everything. I understand that is more reassuring. My view is such that I don't believe that uncertainty will disappear in the future. I believe that uncertainty is really part of the system, is a reason of its life. I understand that my view may be more depressing because, I mean, we feel more reassured if we are told that we can predict everything. Why people get really depressed after a flood, after an earthquake, and they tend to attribute the responsibility to something, like it happens an earthquake, so who is the fault? Okay, because people is reassured if they can predict everything. Why? Also with the human health, people are reassured if they are told that we can predict everything. On the other hand, if you think of a situation in which you can predict everything of your life, including our final day, this is really something depressing, because I don't think that we need certainty to make a strategy, to make to get protected against the risk, against the human nature. I don't think we need certainty, because once that we get a good estimate of uncertainty, as I said before, as I said earlier, it's fine. It's what we need. We don't need certainty, because certainty would be misleading. It's not possible. So, I mean, don't get like disoriented if one puts in evidence that there are several things that we don't know. The important thing is that we gain the means to treat these unknowns. And models, this is their purpose. If a model is not precise, it's not useless. It is very useful. So let's talk about models. Okay, let me get the PowerPoint here. Okay, here we are. So look at this figure, and it is public domain. I think it is really a good illustration of our model work. You see cells, elementary volumes, elementary cells, and a grid. A grid in 3 dimensions, so they are elementary volumes actually, not cells. They are cells over the surface, but then there is the 3rd dimension. And these cells occupy the atmosphere, but also the land. And this is why you can see both the land and the atmosphere here. Atmosphere, of course, because we describe the climate system, but also the land, because the land-atmosphere interaction is an essential component of these models. And actually, when I say the land, I'm also implying the land for a depth, so in 3 dimensions, because we need to include the groundwater cycle, we need to include also processes that are taking place into the soil. Usually climate models don't go more in depth than the soil. Okay? They describe the soil because the soil is part contributing to the water cycle. They don't describe the movement of the core. Okay, the movement of the core is dedicated to, is studied by other models. We have models to study the movement of the core, but usually they are not linked to the climate models. And the same for hydrology, as I said. The land is also studied by hydrologists, but the models are conceived with different purposes. So hydrologists want to study the water cycle for water resources management, for making prediction about flooding, droughts, and it's a subset of climate. And therefore, and also they don't need to go at the global level. Hydrologists study the water cycle by taking rainfall as an input variable. So usually they can work at local scale. They don't need to describe the dynamics of rainfall. They get rainfall as an input variable through data, for instance, and therefore they can work at local scale. So these models that are studied by the hydrologists of the water cycle are much more refined than the climate models. Their scale, a level of definition of processes, an hydrologist takes into consideration the shape of the riverbed. Climate modeler doesn't take into consideration the shape of the riverbed. Okay, hydrologists look for the shape of the levee. In a climate models, you will not find anything related to that. But actually, I mean, when we want to describe the effect of climate at the global, at the local level, we need to look at the shape of the riverbed and the levees. If I want to estimate when land gets flooded or not, I need to describe the levee. And this is something that frequently I discuss with my colleagues working on climate science. They say, look, we are already taking into account hydrology. And then I say, okay, so are you taking into account of the levees? And they say, no, absolutely, because I don't need them. And my reply is, yes, but if you want to model flooding, you need to take into account the shape of the levee. It's a human intervention. It's like CO2 emissions. So you understand this convergence between models is not easy. Anyway, this is a good sketch, and look at the physical processes here. Atmosphere, snow, rainfall, ocean circulation. It's extremely important to shape climate. Ocean circulation is essential. And then we need to describe also the fluxes of water from the land to the ocean, evaporation, solar radiation, sea ice, cryosphere. These are the processes that you need to include. Okay, so I think we can skip this because we already discussed this. So typically a model has an input and generates an output. Here you see a representation through a black box. Black box is a synonym of empirical model. Actually, we already said and we already know that our model is not necessarily a black box, maybe physically based, chemistry based, etc. And why did humans start to make models of climate recently, but not very recently, because the first models were devised in the 19th century, very simple models, but they were already physically based. I will show you an example. And the big jump occurred around 1960 with the advent of computer simulation models. Okay, here you see 1950s. More or less, these were the years. Keep in mind that in 1950, the supercomputers, which typically occupied an entire room like this, were less powerful than this computer that I have now here. They were worked with very long computational times. they used paper cards in order to instruct them. And then around 1980, 1990, there was a big jump in the computational capacity and in the availability of computers at the scale of a single home. There was a big jump from 1985 to 2000, and from 2000 up to today, we had improvements, of course, but not so relevant as in the previous period, the 1980 2000. We had an improvement, but again, not so relevant. And for instance, today, when we talk about supercomputers, the supercomputers basically are a big improvement, but this big improvement has been reached by putting in parallel several computational machines, which individually taken are not much more powerful with respect to 20 years ago. So the progress has been made in the size, the dimension of these computers. They are smaller now. Like, for instance, if you look at the computational unit here, it's like very, very tiny, and this allows to put several of them in the same room. Still, these supercomputers absorb a lot of energy, really a lot of energy, and they make a lot of noise because they need to be cooled down, and there is a lot of noise, of complications. And by the way, what is the reason why? As you know, in the past 2 years, artificial intelligence has become so popular, like a new thing, a new tool. Actually, it's not a new tool. 20 years ago, we were already working with the same models that are now working to generate artificial intelligence. So what is the difference? The difference are the supercomputers. So with the availability of many supercomputers, now we have the possibility to crunch a lot of more data in a reasonable time. So this is why ChatGPT can answer so many questions in a very limited time, because it gets computational resources from supercomputers that can analyze a lot of data. Okay. So it is the volume of the computation that has allowed to generate artificial intelligence. Okay, and so we need to describe several processes, and we already talked about the spheres. Okay, and these are the spheres of the Earth system that we need to describe: the atmosphere, the cryosphere. There might be many others, but typically these are the top ones that are modeled into a global model of climate. Atmosphere, cryosphere, hydrosphere, it's the domain of water. The biosphere, the domain of the living organisms, and the technosphere is the domain of the technology. If we look at the atmosphere, here you see a representation of the different strata, different layers of the atmosphere. This is not very relevant for you for preparing your exam. The name of these layers are just given to you for your information, because I myself sometimes don't remember when I talked about the thermosphere or the mesosphere, if it is in an upper position with respect to the stratosphere. Just remember one thing: the layer that is closer to us is the troposphere. This allows you to better understand when you need something, okay? But you will not find a quiz on like a question like the troposphere is lower or an upper position with respect to the stratosphere. Okay. I think we already discussed this, and just remember that this you may find a question in your quiz about what is the surface of the oceans with respect to the surface of the land, and the alternatives are well distinguished. You will not find something like in the alternatives 61, 70, or 71. You will find these alternatives, oceans are 10%, 50%, or 100% of the global Earth surface, something like that. Just remember the order of magnitude, okay? It is important. Also, another order of magnitude that I already mentioned to you, and you have to remember, is the percentage of fresh water with respect to the total water. We said 3%, more or less, okay? Yeah, let me just spend a few words about the technosphere. This is interesting because first let's read the definition. The technosphere, like sometimes referred as anthroposphere, is that part of the environment that is made or modified by humans for use in human activities and human habitats. Okay. So the cities are part of the technosphere. The railways are part of the technosphere. The airports are part of the technosphere. It is also called anthroposphere, and an interesting reasoning, an interesting discussion, not reasoning. You may have heard that some scientists, typically climate scientists, are proposing to change the name of the current era from Holocene to Anthropocene. Why? Because they believe that the human-induced changes over the Earth system are becoming so relevant to justify the introduction of a new era, geologic era. Typically, these eras, these periods, these epochs, they are defined in different ways, eras, periods, epochs. But these time windows are marked by geological changes. So basically, they want to identify, to start a new era, the Anthropocene, a geological marker of the human action. So climate scientists believe that indeed there is already a geological marker. Geological marker means that when you make a stratigraphy of the Earth, you recognize it. Okay. Now, you may know that there is a huge debate that so far the proposal was not approved. The international scientific community didn't approve that. Because, especially the geologists, they struggle to recognize the geological marker of the human activity. So they say, if I look at the stratigraphy of the Earth, which means that you don't look just at the surface, you go quite in depth, I don't find a difference, I don't find a marker where the human action can be recognized. I see the marker of the human action in the soil, in the surface, or maybe up to a depth of like 10 meters, 15 meters. But I don't see in the stratigraphy a marker, so it's not justified. Because typically these markers are created by a change in climate. Change in climate means that, when we hadn't ice caps, or when we had volcanic eruptions, really important ones, they cause the change in climate. And so there is still some doubt about the changes in climate that we are experiencing today. Their effectiveness has a geological mark. And this is really an interesting debate that is ongoing. Like, okay, atmosphere, human-induced changes, but are they so relevant? Are they really capable of changing the Earth system in a way that can be recognized even in the deep Earth? It's a very interesting debate, and I got to review a scientific paper recently by authors that were indeed advocating that we need a new era. Okay, it is interesting. I'm not an expert, so I don't have an opinion. I recognize that starting a new era may have an effect in communication. Okay? And I recognize that indeed it's important to communicate that the human influence overall is important. I would say that it is very important for humans. The human influence is more relevant where the human lives, of course. The humans live, of course. And therefore, the impact on the humans themselves is really important. And we have to convey this information. Like, if we want to think of the future of humanity, which perhaps is more important than the future of the Earth system. Okay, if the Earth system dies, also human die. But I think that human may die and the Earth system may continue. So if we are interested in the future of humanity, indeed, the human impact is much relevant. And we should be able to convey this message. I am not sure, as a non-expert, of the effectiveness of the message if we claim that there has been a change that is geologically relevant. Because I'm not really sure. But it is for sure relevant, the change that we are causing on the habitat of humans. It is for sure relevant. We mentioned the cities. In some of the cities, we had an increase of temperature of 5 degrees. 5 degrees means a lot. If you talk to an expert medical doctor in geriatry, they tell you 5 degrees, it's a big difference. By the way, 1 week ago, I had a conversation with a medical doctor, one of my colleagues that is an expert on global health. And he told me, look, it is really complicated to understand the impact of warming on the human health, because he said, first, you have to take into account that, yes, indeed, even an increase, he said, even an increase of 1 degree during summer causes the death of people. There is no doubt on that, he said. Even just 1 degree. Not to talk about 5, but he said, even 1 degree causes the death of people. There is no doubt. On the other hand, he said, in a warmer winter, typically people die during the winter, not during summer. But he said, if you look at the statistics, and you look at how many people die in the world, and the percentage of people dying during the winter, they typically die during the winter, with a larger percentage. And with 1 degree more during the winter, then you may save more people than those who die during summer. So this is a first complication, he said. First complication. Second complication, he said, it is difficult to maintain a position where the human influence has caused an increase of mortality. Because it is impossible. Actually, the science has caused, has benefited, has fruited a decrease of mortality. Because if you look at the average duration of the human life, it is for sure increased a lot in the past 50 years, but really a lot, he said. Like also in Italy, if you look at Italy, like in the past 20 years, at least 5 years on average. And therefore, it is not tenable that we say after global warming, there has been an increase of mortality. On the other hand, he said, clearly there is a limit to this improvement. And in the future, we can predict that the average life will not increase in the next 30 years of more, 25 years more. It's impossible. You get close to the limit, it's asymptotic. And therefore, he said, in the future, it may be that the effect of climate change gets larger, more relevant than the effect of the progress in medicine. But he said, look, to make a prediction is really difficult. It's really difficult. So he said, I'm not sure that if we increase 1 degree more, there will be an increase of mortality. Maybe that the gain for less death during winter is higher. Okay, so I think we can move forward. We already talked about this. Just keep in mind these numbers, okay? 97%. Okay, here you see 96.5, but then there is 1% more of other saline water. So usually I say 97% is salted water. On the other hand, I don't remember if I said this. The amount of water that we can use, which is basically this part up here, which is like 0.01% of the total water. So the amount of water that we can use for human use is large enough to feed a much larger humanity of what we have now. Okay, so we have enough fresh water even without desalination. What is the problem? The problem is the distribution in time and space, and in particular distribution in space, because water has a problem, it's heavy. And we use a lot of water, so the volume is large, so we cannot move water for human use. This is impossible. Even if now there are researches, and you may find over the media people that are researching on studying efficient methods for moving water, but actually there is no future in that. Okay, so it is for sure more efficient to desalinate rather than bringing water from Sweden to Italy. The south of Italy is absolutely impossible. So the spatial distribution is a problem. The temporal distribution is another problem, but it is more solvable because with artificial reservoirs, we can store water and compensate the uneven time distribution. Okay, now remember that the engine, the fuel for the climate system is solar energy. And let's try to understand how it works. We already showed figure on how it is split, the contribution by solar energy into the Earth system. So some of the solar energy is reflected back into space, while the rest is absorbed by the climate system and re-emitted as heat. Part of it is also absorbed by the land, and part of it is re-emitted in the atmosphere. And at the end, part of the reflected and re-emitted energy is trapped by the greenhouse effect. And we have to describe this energy flux, not only this, but this is a sub-process that we need to describe. Okay. Now, let's try to understand something more. Earth is heated by the sun in an uneven way, of course, as some parts of the Earth receive more energy, and therefore there is energy imbalance. Energy imbalance means temperature differences. And the system tends to reduce these temperature differences because the system try to compensate, of course, try to reach an equilibrium that is close to the average. And how it is reduced, this imbalance? By transporting heat from the warm parts to the colder parts, and in particular, transporting heat from the tropics to the cool ice zone of the poles. And this originates the ocean currents, originates the winds, originates evaporation, precipitation, and global circulation. Global circulation of what? Of matters. Global circulation of energy, global circulation of heat, global circulation of water. And these global circulations are a key to model the climate. And I want to give you an example which is related to, I'm not sure if I have a slide, just 1 second. No, I don't have a slide. Okay, let me just. Okay, let me give you an example of a global circulation pattern. So let me get, not here, let's get here, okay. El Nino, okay, you heard about El Nino. And let's see, El Nino English Wikipedia. Okay, and let me, I think, this is the picture that I wanted to show you. Okay, so this is the Pacific Ocean. Here, the Pacific Ocean. Now, when you have a situation of imbalance in the temperature of the ocean, this is just 1 second. Okay, when you have an imbalance, so a warmer part, and this is the west part, okay, and the cool part, the east part. So this is Australia, and this is South America. And because we look at the southern Pacific Ocean for El Nino. So when you have warm climate in close to Australia and cool ocean close to the South of America, an ocean circulation is originated, which causes from the deep ocean a flux of water to South America, to the South American coast, and in the upper ocean an opposite circulation. So we have this kind of circulation, which originates evaporation close to Australia and dry situation in the South of America. This is precisely El Nino. Oh, sorry, this is La Nina. So this is, when it happens El Nino, it's the opposite. When it happens El Nino, then we have a cool ocean close to Australia and warm ocean close to South America, and dry climate in Australia and wet climate in South America. So when you have this situation that you see on the screen, La Nina, you get flooding in Australia and drought in South America. What is the reason of this imbalance? It's a particular climatic situation that cannot be predicted. We know on average how many times, what is the frequency of La Nina and the frequency of El Nino. And usually we get an anticipation of a couple of months before the occurrence, because we start observing an imbalance in temperature in the Pacific Ocean. And then we know that when this situation starts to develop, may be likely that it will continue. So usually, for instance, last autumn season in September, I read on the web because I am interested, so I checked the El Nino forecasting. I read on the web there is a high probability of La Nina during winter, which actually occurred. It was not very strong. It was what we are experiencing now. There is a La Nina that is ongoing. It's not very strong. But this allows us to, in a way, to predict with some couple of months of lead time, these conditions of drought or flood, either in Australia or South America. The nice story is that the influence, the impact is not only confined to Australia and South America, but there are implications in the global climate. These implications are not fully understood. So they are based on a statistical analysis. So what happened during past La Nina? And we know that during past La Nina, there are evidences that the south of Italy underwent a dry winter. This is not always like that, but in most of the cases, we have a dry winter. Of course, the effect, the impact in Europe of this circulation pattern You understand why circulation pattern? Because there is an implication in the circulation of water. And we know that it's much lower the impact in Europe, but still there is an impact. But this is only an example of a global teleconnection index. Why teleconnection index? Because it's a teleconnection between different climatic variables. In this case, is connection between the temperature of the Pacific Ocean close to Australia and close to the coast of South America. So basically, the variable is temperature, and we start the connection between these two temperature indexes. So they are called the teleconnection indexes. So El Nino, which is called also ENSO, which stands for East Southern Oscillation. I don't remember the meaning of the acronym, but this is indeed one of the many teleconnections. There are many others. This is the most famous because the effect on Australia and South of America is clear, it's very evident. The other teleconnection, the effect is weaker. So there is, for instance, the North Atlantic Oscillation is a difference in barometric pressure between the Arctic and the Azores. So we know that when there is a huge difference in barometric pressure between the Arctic and the Azores, then there is an ocean circulation in the Atlantic that is triggered. And it has an implication on climate. For instance, when there is a huge difference in these barometric pressures, we know that the south of Italy experiences droughts rather than wet seasons. There are several of these teleconnections that are available that are being studied. Usually in climate models don't fully represent them, okay? Because it is a level of detail and their connection with the climate is still too poorly understood, okay? But it is extremely interesting, extremely fascinating also to study these analogies, connections between the outcome from weather and large-scale variables, large-scale state of the atmosphere and the oceans. Because if we could gain a better understanding of these connections, we could make like seasonal predictions. And for droughts prediction, for instance, it would be extremely important. But again, climate models don't reproduce the complete set of these teleconnections. Let's make now a break of 15 minutes, and then we open the next hour with the question and answer. At least 2 questions. Prepare, please. Okay. Otherwise, I continue teaching until you ask 2 questions. Okay. See you in 15 minutes. Okay, questions? Usciamo. Yeah?
And so, like, why don't we get there?
Can you please repeat? Because I think I got it, but I lost it. What it means? Yeah.
Make the power is much more.
Okay. Yeah,
To be used in.
because, okay, first, my view on the nuclear power changed a lot. In the 1980s, in Italy, we had a referendum on the opportunity to close all of our nuclear powers, and I voted for closing. Because at that time there were a lot of concerns on the safety on after Chernobyl in particular. I think we had the referendum before Chernobyl or soon after Chernobyl. So the Chernobyl accident indeed was something that changed completely the fate of the nuclear power at the global level. So I was concerned, and I thought that it was not needed because I was convinced that, with the international socioeconomic setting that we had at that time, I was convinced that we didn't need it. Now I am convinced that we need nuclear power. So there is a debate in Italy ongoing, because of course Italy is not very large, so we don't have so much room for hosting nuclear power plants. But I am convinced that it is the solution for the future if we want to move towards decarbonization. Otherwise, with the only renewable, it's not possible, because the renewables are not cannot be regulated, And energy has a big problem that you cannot store it unless you use hydropower. But hydropower, in terms of electricity, hydropower at the global level accounts for about 16% of the total production, which is indeed, it becomes significant. But when you talk about the global energy production, so not only electricity, hydropower is about 3%. Hydropower can be regulated, because by storing water, you can, in a way, decide when you combine it. But it is the only renewable that gives this opportunity. So in terms of only renewables, solar power, wind power, we cannot really cope with the increasing energy demands. So I think that the only possibility is the nuclear power, even without cold fusion. Probably in the future we will get to cold fusion, which will be a very clean way of producing nuclear power. But even without it, I think that now we have some safety conditions that are really reassuring. And above all, I am convinced that decarbonization is indeed something that we need to achieve. Maybe not in the very short term, not so quickly as the European plans are predicting, but in perhaps maybe longer term, I think we need to move towards decarbonization, because it's not only a problem of climate, it's also a problem that we will run out of fossil fuels. And there is also the problem of the urban pollution, which is extremely relevant in my opinion. And for some reason, it is not considered so much. There is a lot of attention on warming. I think it is urban pollution is making more damage in terms of also public health than the warming. So I really think that we need to move significant steps towards decarbonization, and I think nuclear power is the only possibility. And I don't think I changed my mind a little bit. Also, thanks to the technical advances, I don't think it is so dangerous. It's still a bit dangerous. And another thing that I am not really very convinced is electronic cars. I don't think, electric cars. It's too early. It's too early. because now it's extremely costly. So if you impose electronic cars in 10 years from now, as the EU is planning, it is extremely costly, and it is inconvenient in terms of maintenance costs. It is really something that is stretching a little bit too much. And the energy, I mean, now, if we, for producing energy, we still rely a lot on fossil fuels, so it doesn't solve the problem. But it is, I mean, it is not easy to gain an opinion on these issues because we lack the information, actually. So this is information that is related to the geopolitical situation, the possibility of trading energy, because energy can be transported, it's not like water. And so we lack information on the geopolitical situation. So basically we can get feelings, and I can get the technical feeling that it's probably too early to decarbonize completely. But actually the information that we have available, you know, the most important information is secret, so it's not easy. Other questions? Okay, one may be enough. Even that, I think it was you asking that. No, the other person. No, there was a question and one by you. Correct? Yeah. Okay. Good. Okay, so let's move a little bit forward in our understanding of how models work. And again, the importance of chaos. This figure is just to remind us what is chaos. And chaos implies a high sensitivity to initial and boundary conditions. So even a small change in the initial condition, like a butterfly flipping the wings in Japan, may determine a huge change in the final result. This is why the climate system is difficult to predict, because chaotic system may be predictable in the short term, but not in the long term. And sometimes even in the short term, the prediction is complicated. Chaos is usually dealt with statistical approaches. And keep in mind one thing, that when we mix, when we talk about statistical approaches, it's possible to inform statistical approaches or any kind of data-driven model with physical basis. So again, also in this case, there is an in-between between the statistical models and the deterministic models. The in-between is that the uncertainty that can be reduced is indeed reduced by using physical knowledge, and only the part of uncertainty that is left after we use the full of our physical knowledge is dealt with statistically. And this is, in my opinion, the way forward. So if we have to use a mixed model, what we may call like physically based statistical models, which means that we use our knowledge as much as possible. We use physical laws as much as possible. And then we use statistics to deal with the remaining uncertainty with flexibility, because in the future, our knowledge, our physical knowledge may improve. And then after the improvement, we refine our models and reduce the part of uncertainty that we cannot predict. And in doing that, in setting up an integrated approach, we gain flexibility, as I said, and also studying uncertainty may help us to understand what are the physical gaps, what are the knowledge gaps where we have to work on. Okay. Just 1 second. Yeah. Okay, so let me move forward. I'll come back to this slide later. Let me move forward again to this figure. So global climate models are also called GCMs. It's the acronym for Global G Climate C Model. And so we call them GCMs, and the counterpart are the RCM, regional climate models. Why do we need the regional models? We need the regional models because if we want to describe some processes like convection, we need to work at very fine resolution, spatial resolution. Very fine means like 3 kilometers, 1 kilometer. Typically, GCMs work at a scale of 25 kilometers or 15 kilometers, the most recent ones. If we want to go to the regional scale, then we need to describe processes with a finer resolution, and therefore the computational demands increase. So even in this case, a kind of mixed approach is used where the global model gives the boundary condition to the regional model. So we run a global model to determine boundary conditions. And then we go to the regional models by using those boundary conditions. Let me just spend a few words on these two terms. Boundary conditions and initial conditions. Some of you already know what I'm talking about, but I think it is important that we gain a full understanding of the meaning of these conditions if we really want to understand how models work. So first, these laws of physics that I often mention, the deterministic laws that form the skeleton of our climate models, are very often expressed in differential terms. So they are equations, and I try to simplify because we don't need to get into the mathematics of it, but we need to get an understanding. Like when you basically drive a car, you don't need to know in details what's happening into the engine, but you know to gain an understanding, which means that you know when you can maybe surpass another car because you know how the car works, what is the potential of your car. And in the same way, if we want to understand how climate works, we have to gain an understanding of the concept. Okay, so this is why I'm spending time, but we are not interested in the math. So I try to make it simple. So what does it mean that an equation is expressed in differential terms? Differential terms, okay, means that if you want to describe, for instance, temperature, your analytical relationship doesn't describe temperature directly, but it describes the changes in temperature. Delta, the change. And the change can be described in space and time because these processes depend on space and time, two independent variables, okay? So basically, once again, the way these physical laws are formulated often allow us to describe the changes in space and time, which is fine. Because when I want to model climate change, actually, it is change that is interesting. So it's not a limitation, it is fine. But on the other hand, there is the mathematical additional complexity. Because of course, it would be much better to be able to describe the temperature directly. So, I mean, there is an additional complexity. which is okay. I mean, no problem, because we have specialists, we have mathematicians that can, in a way, solve the additional mathematical complexity. And there is another thing that is important, which is a drawback of working in differential terms. If you want to describe the actual temperature, the difference in time and space is not enough. You need to sum these differences in order to get the temperature. So if I know that tomorrow there will be 1 more degree in Bologna with respect to today, and the day after tomorrow, another more degree, I have to take the sum. If I want to get the change between now and 2 days ahead, I need to make a sum. This sum is called an integration. But there is more to say. If I want the real temperature in Bologna in 2 days ahead, and I only know the change from today, I also need to know the temperature of today. And I get the temperature of today is 16, perfect. And I know that tomorrow there will be 1 more degree, so I take 16 plus 1, and the temperature of tomorrow is 17. But I need this value of today's temperature. This is what we call initial condition. To say that it's very simple. I mean, if I have an equation describing the change of temperature in Bologna between today and tomorrow, and it is 1 degree, and I want to know the temperature of tomorrow, I also need to know the temperature of today. This is the initial condition. So you understand what it means, a model that a tiny change in the initial condition may cause a big change in the final result. When I talk about initial condition, now you understand. It is a kind of starting point in time, an observation that defines an observation or an assumption that defines the starting point in time. In the same way, I may have an equation describing the change in temperature between Bologna and the Adriatic Sea today. Okay? So if today I want to know the temperature over the Adriatic coast, and I know that it's 2 degrees more than the temperature in Bologna, because my model only describes the changes, I need to know what is the temperature in Bologna today in order to get the temperature on the Adriatic coast. And this is the boundary condition. So boundary is a starting point in space, and I start from the boundary. And initial is a starting point in time. Is this clear? So when I say we need initial and boundary conditions, this is what I mean. And this is something that typically the model doesn't have. It's an input variable. It's an information that we have to give to the model. And this is important because the temperature change in Bologna from today to tomorrow depends on the initial condition, depends on the temperature of today. If I tell my model today there are 0 degrees, the prediction of the temperature change between today and tomorrow is different with respect to the situation in which I tell my model today is 16. These are input data. Now, what is the boundary of my original model? It is given by the global model. The global model gives the boundary condition for the regional model. So typically in Emilia-Romagna, this region here, we have a regional model for the region. And we get the boundary condition and the initial conditions. For instance, temperature tomorrow in Bologna from a global model. And also the global model needs an initial condition. And needs also boundary condition that is self-computed by the model. Now, What then a model does at each one of these elementary volumes, the model applies the laws of physics or the laws of statistics, whatever it is. Typically, when we work at very fine resolution, it is a physical model. It is a physically based model that we use. So at any cell, at any of these elementary volumes, the model solves the equation of physics. Of what processes? Everything we need. Ocean circulation, hydrology, water cycle, everything we need. Typically, these equations expressed in equation terms are balance equation, energy balance, mass balance, what are called conservation equations. So at each of these volumes, we describe the conservation of energy, the conservation of mass of what? Of water, for instance, or mass of carbon, any matter that is exchanged between these volumes, any matter that flows in the atmosphere, in the Earth system. So this means that at each volume, we have this set of equations that are applied. And each volume does need to get the boundary condition from the neighboring volumes, because there are fluxes of matter. So there is water passing from one volume to the next. And we need to describe this flow through boundary conditions. This means that given that the boundary conditions depend on the equations of the other cells, this means that all of these equations, like 3 equations for each volume and 50 millions of volumes, this equation need to be solved together. So you understand why we need supercomputers. Because we have millions of equations conditioning each other, and they need to be solved together. And then you also understand uncertainty, because clearly, when you have millions of equations, even if you have a very small uncertainty for each of them, at the end of the story, you get uncertainty, noticeable uncertainty. And these are nonlinear equations, chaotic systems. Nonlinear means powers. So there are powers in the equation. What happens? Why do we split in elementary volumes? You could say something like, but couldn't we use a unique volume? Why do we need to split? This is an interesting question. Why do we need to split? The reason why we need to split is that we want a local definition. I try to better explain. If we use a unique volume for describing global temperature, this is the average temperature, because any volume is described through physical laws that apply to each of them, and they give one value of temperature in the volume. They cannot describe the variability within the volume. The volume is considered an elementary volume to which we apply these equations. So if I get only one volume for the full Earth system, I get only one value of temperature. There is no possibility to describe the heterogeneity within each volume. And this is why then we need to split our overall volume into elementary volumes if we want to describe the variables at local scale. So if I just wanted global temperature, global precipitation, that's fine, I can consider a unique volume. But if we want to go at the local level, we need to split into so many volumes. And I mean, the computational time for these models is relevant. It's days, weeks. So this is why sometimes it's difficult for us to launch several simulations, even with supercomputers. The number of simulations that we are able to launch, it's limited. Okay. You see that modern, what is the size of the cells, the volumes? Okay, modern models, here I reported an area over the surface, over the land, of these elementary volumes of about 100 square kilometers, which means 10 by 10. Earlier I said 25 by 25, 15 by 15. Of course, the resolution is increasing depending on the computational resources that we have available. And okay, here it says what I already mentioned, like candidate equations are conservation laws. And basically, conservation laws state that a particular measurable property of a physical system does not change as the system evolves over time. And so conservation of energy means that if you compute the global budget, energy is conserved. And the same for the mass of other matters, like, for instance, water, and other quantities like momentum, energy. So by imposing the conservation of these quantities, be careful. Conservation means that, for instance, if you get a volume and you consider the mass of water, conservation of water within a volume means that if you compute what the mass of water that is getting into the volume, the mass of water stored into the volume, the mass of water that goes out, so the difference input minus output is equal to the change of mass stored. So you understand why then the equation is expressed in differential term. I explain again. I have a volume, water getting in, water getting out. Difference in minus out is, for the principle of conservation of mass, equal to the change of mass stored. And you understand why it's in differential terms. The conservation equation typically is in differential terms. So it doesn't mean that the mass doesn't change. It means that it's conserved. So the stored mass of water may change, but the total mass of water is conserved by taking into account the volume that comes in, the mass that comes in, and the mass that comes out. Is it clear, or it's too complicated or too simple? Maybe it's clear. Do you have any question? Okay. Okay. So what do they do essentially is to describe how energy and materials propagate through the climate system. Sorry, I give a look at the chart. Okay, no problem. Climate system, which includes atmosphere, land, and oceans, and just let me say one thing, which is propedeutic to giving you an example of a simple climate model. You can simplify it. I mean, if you are not interested in describing at the very local level variables, you can reduce the number of cells. And if you are interested in describing only global temperature, you may just consider one unit volume. I give you an example. It becomes very simple. So in a way, you have flexibility. And you may introduce assumptions if you want to simplify, like I discard selected processes. I discard uncertainty. This is possible. You get just 1 point prediction. You know that it's uncertain, but you don't want to estimate uncertainty. which is, possible. Okay, so of course you need input data. Input data is solar forcing is the main one. And also you need the concentration of CO2, you need emission scenarios in order to understand what is the future concentration of CO2. And keep in mind that this input data sometimes are not easy to be retrieved because like for instance, initial condition, boundary condition, maybe a lot of data. You want to define the initial condition with observations. You need to provide initial conditions to each of the cells, which means a lot of data. And in the past, we had problems because we started monitoring the climate system only recently. So it was like a problem to identify the input data. Today, we have a lot of Earth observations that are coming in, thanks to the use of satellite remote sensing. Actually, today we have the opposite problem, that we are getting every second tons of data which we cannot digest. And this is where artificial intelligence may indeed help, because we have these huge databases that are becoming available, and it is not easy to incorporate them into our models. And therefore, there are opportunities in this respect, and this is recognized as a very relevant research challenge, how to make the best use of this relevant information that we have available today. Just 1 second, okay. Yeah, let me give you an example. And I stepped forward a couple of slides because I think it's important that I give you an example at this stage, and then I go back with the 2 slides that I skipped. Let me give you an example of a climate model, because I want to demonstrate, I want you to understand that, if we reduce the number of volumes, it becomes very simple. This is an example of a climate model that was introduced, like, I think it was in the 19th century, to compute the average temperature of Earth. So this was the target of this model. What is the average temperature of Earth, where average is meant in space and time? So we are not interested in a particular location, global temperature, and we are not interested in a particular time scale. It's in the long term, okay? And therefore, a simple equation can be written, which is a balance of solar radiation. So it is using the concept of radiative equilibrium. Let's look at the equation because it is very simple. So what is the meaning of the variables? You can see it here. So we have S, which is the solar constant. It's the incoming solar radiation per unit area. And we know more or less its value in the current time. Okay, it's about 1,367 watt per square meters. This is energy from the sun, okay, also called solar radiation. Okay, this solar radiation is multiplied by pi and the radius squared of Earth, which means the global Earth surface, okay? And then we need to take into account the albedo, and the albedo is the part that is reflected back into the space, okay? Which is about 0.3 is the average albedo. So basically, we take the global energy from the sun, multiply it by 0.7 to take into account what is retained by the atmosphere. Perfect. Now, this is the incoming one, and the right-hand side, we have temperature at the power of 4, okay? In order to compute, to make an energy balance, we need to take into account the temperature to the power of 4. we need to account sigma, which is the Stefan Boltzmann constant, and then there is epsilon, which is the emissivity of Earth. And if we multiply this by the surface of Earth times 4, we get a balance equation. And let's forget about the details, because you could ask me what is the Stefan Boltzmann equation, what is, okay, let's forget about it. Just let's take for granted that in order to that this increase of energy from the sun, and this flux of energy from the sun is related to temperature according to this equation. And then it is very simple to take, to derive an explicit representation from temperature, which is given by this formula here. So temperature is equal to the root to the power of 4 of 1 minus A times S divided by 4 sigma epsilon. And if you compute it by substituting these values for the various constants, then you get this value of temperature, which is about 15 degrees, which is true, because the average temperature of Earth is about, 14 and a half, varying from 14 and a half to 15, depending on the time at which you make the computation, which is correct. And this is a very simple balance, energy balance, applied at the global level that allows us indeed to compute, basing on observations and basing on our knowledge of these constants that were computed empirically. We can, in a way, compute the average temperature of Earth. And the same computation could be done at the local level. Of course, at the local level, you have to compute the local value of the solar radiation, and it may refer to the long term, or it may be referred to a specific season, for instance. And then you have to compute, of course, you cannot use the same equation because this uses the radius of Earth. You would need to define the volume and the surface of the elementary volume that you are considering, and then you have to use the local value. The Stefan Boltzmann constant is constant, but the emissivity of Earth, you have to use the local value. So the computation becomes much more complicated, especially because you need to define these solar radiation and the emissivity at the local scale. So you need a lot of information, which becomes also more imprecise because, of course, when you go into the detail, uncertainty increases. And but it can be applied also at the local level, which is, I think, a useful example. And then let me go back a couple of slides and mention to you that there are several models available which differ, as I said at the start of this lecture, for the assumptions that are made, for the equations that are used. These models, there are several of them, and typically these are all publicly available. So the results, the simulation, the scenarios are publicly available. It's not easy to use them because it's a huge amount of data. And if you want to download them and analyze them, it's not easy because you have to deal with trillions of numbers, but they are available. If you want to get information on the models that are mainstream today, and also what are the variables that they simulate, because there are a lot of things: barometric pressure, temperature, rainfall, river flow. The modern models also simulate river flow, or let's say contribution to river flow, local contribution to river flow. Then you may refer to the IPCC report. And also, if you want to jump directly to this kind of information, if you Google for CMIP, which is the Carbon Model Intercomparison Project, you get directly to the data storage. And another Another keyword for Googling is just 1 second. Let me just get another browser. Okay, let's Google for Copernicus data, climate data store. Okay. Now I don't want to open a browser now, which we are closing. Which will give you these informations also to this information is useful also for getting additional details on the time resolution, spatial resolution, and the most recent contributions regarding the development of climate models. I think we are getting close to our closure today. Questions?